Greetings, scholars. This is a tutorial video on a spreadsheet called balance point temperature. I'd like you to pay real close attention to this one. The overall idea is that inside every building there is heat gain from people, lights, and equipment. In order for the building to be in thermal equilibrium, in other words, to maintain temperature without additional energy, it has to be colder outside than it is inside to drive heat loss through the skin of the building, the walls, the glass, the roof, the doors, the walls, and by infiltration, right, or air change of one sort or the other. Either we accidentally lose air through cracks and openings, or we purposefully change air by mechanical ventilation. So for these two things to be equal, it has to be colder outside. Now generally we assume that it's about 65 degrees inside during months when it's cold outside. Remember, it has to be colder outside than inside to determine our thermal equilibrium balance point temperature. So we need to find that balance point temperature to know something about the relation of the building to the climate that it's in. Now, to calculate internal heat gains, if we look at lights, equipment, and miscellaneous loads like plug loads from things we plug into the wall, we can assign those densities. So if we had 1 watt per square foot of light, in other words, a 100-watt light bulb in a 100 square foot room, and if we had half a watt of equipment and appliances in there, and we had 0.2 watts of plug loads, let's say, for a clock and other little things, and based on a building of 2,500 square feet, if we also had 2,500 square feet of occupied area, and they might not be the same area, but let's assume they are for now, we would find the occupant density by code, in this case 80 occupants per 1,000 square feet, which tells us that there are 200 occupants in the building. And we would look up how much heat each occupant contributes in terms of sensible load, that's temperature type body heat as opposed to latent heat from the moisture that they leave in the room. And that gives us some totals. This is our total internal heat gain from lights, equipment, and miscellaneous things. And this is our internal heat gain from people. Generally in balance point we ignore solar gain, but we could, if we wanted to calculate solar gain, enter some values here for a particular time of day, time of year. Now, we need to know the rate of loss between the inside and outside, and that's dependent not only on the temperature difference but also on the amount of insulation between the two. And if we know the amount of heat loss, the rate of heat loss, to air change, either by ventilation or infiltration. In this case, we're going to set it up by per occupant, so it's based on ventilation standards. Then if these are the rates of loss, which are temperature driven, and these are heat gain items, which are not temperature driven, they're temperature independent, then we can say how much temperature difference is necessary between inside and outside for these two things to be equal. And because we already know the inside temperature, if we know the temperature difference, we can then determine the outside temperature, which will be our balance point temperature. So note that in this particular example, for this amount of heat gain from people, lights, equipment, miscellaneous, and solar, which is 0 in this case, to be equal to the amount of heat loss to the outside, it would have to be about 19 degrees Fahrenheit outside for the building to ever need heat. Whenever the outdoor temperature is below the balance point, okay, the building will need heating. whenever the outdoor temperature is above the balance point, within, say, 5 degrees, the building will need some sort of cooling. Now, we don't always need mechanical cooling, because between the balance point temperature and about 55 degrees, we can use outdoor air to provide 100% free cooling, right? We just use 100% outside air, and that's enough to cool our building. Think of this in terms of your own personal comfort level. You have a certain amount of internal heat gain from your metabolic calorie consumption of food, and you have heat loss to the outdoors by convection, conduction, radiation, evaporation, limited by how much insulation you're wearing. And the more active you are, the more internal heat gain you have. So for the same level of insulation, it would have to be cooler outside for you to be in thermal equilibrium. In other words, for you to be comfortable. As you increase your insulation level, it also has to be colder outside, a lower balance point temperature, for you to reach the comfort level. So that's the fundamentals of what this spreadsheet does, is it lets you input some ideas about your building and the rates of internal heat gain, solar gain, which normally we will ignore for balance point calculations. It lets you dictate the areas of the envelope components, the skin of the building, and their respective R values, their insulation levels. And you look at ventilation, because outside air, if it's colder than inside air, is going to help cool the building. Find that rate, and we get the balance point temperature. Please note, the spreadsheet has tabs at the bottom. So there's a tab for help. Tells you basically how to use the spreadsheet and what the whole idea is in exploration. There are some definitions of the key concepts here. Then there are tips about what everything means, an example, and some page references in your text. And then there's the input-output worksheet itself. That's balance point.